So you guys, now that we know about radian angle measure, we can talk about the trig functions of real numbers. And you might be thinking to yourself, well, I thought we already were looking at trig functions. Yes, but what was the input of the trig functions? It wasn't what we consider like a distance measurement or a time measurement. It was an angle measure, right? So what we're talking about here is taking trig functions of numbers, of regular real numbers that can represent a distance or a time. And the radian angle measure combined with the unit circle can help us make that connection between trig functions of an angle and trig functions of a real number. So there you go. The main goal for today is to evaluate a trig function of any real number. What are the applications? Well, you know how the sine and cosine are periodic? In other words, if you think about in terms of an angle, if you go around 370 degrees, right, you'll be in the same spot as if you only went around 10 degrees. Now, don't get the wrong idea. 370 degrees and 10 degrees are not the same angle. They're just in the same spot, right? So if you think about it then, the period of the sine, though, and the cosine, if you take the sine of 370, that's the same as the sine of 10 degrees. If you take the cosine of 370, that's the same as the cosine of 10 degrees. So when that happens, we call those kind of functions periodic, when the same outputs start occurring over and over again for certain inputs. We call those kinds of functions periodic. And there's lots of phenomena in nature that are periodic that we can use a sine function, a sine wave. You're going to see it if you graph it in the XY plane. It turns out to be a wave. There's lots of applications in science and in nature of those kinds of functions. So spring vibrations, anything that vibrates, really. Anything in wave form like sound or light might be modeled using some sort of trig function. The tides, the depth at a certain location may be on a pier. That's periodic throughout the day, right? The tide comes in, the tide goes out. The outside temperature throughout the day is periodic. It goes up, it goes back down. AC current is periodic. So all kinds of applications. That's the big idea, by the way. We can use trig functions to model repetitive or periodic phenomena. Now, in order to do that, we need to talk about this idea of a wrapping function. So I want you to recall a couple of things here. The radian angle measure that we defined the other day, remember, if you have a pi, pi. If you have a pi, it's hard to draw a good circle. And imagine that's a circle, and you take out a slice of pi, and that this is your angle that we're talking about, and this crust of the pie is your arc length, S, and in this section we're going to actually call it T, but in the last section we called it S, and then R is the radius. Then we talked about a new way to measure the angle theta last time. We take the arc length, the length of the crust, in ratio to R. Theta equals S divided by R. So that's just, if we call these notes, that's note number one. Recall that the radian angle measure, theta equals S over R. That's the definition. And note number two, you remember what the unit circle is? On the unit circle, what's the radius? 1. R equals 1. So on the unit circle, theta is equal to S. You see why? If R is equal to 1, you just get theta equals S over 1 in radian angle measure, which is just S. So there's a correspondence, an equality between the arc length and theta if R equals 1, if we're talking about the unit circle. Theta equals S, arc length. In this section, we're going to use T. And the idea is that this arc length T, it's the same as S. We were talking about a second ago. This is this crust of the pie here, has length T, whatever units we're in. Then the angle measure on the unit circle, because it's a radius 1, is going to be T as well. So what's the big idea? We don't have to think of it when we start taking sines and cosines. We don't have to think of this angle as an angle measure. If we take the sine of t, for instance, we don't have to think of it as an angle t. We can think of it as a length measurement t. Or t could even stand for time, really, because we often associate time with distance, don't we? Which is kind of weird if you think about it, but we do that all the time. So t can be a real number instead of just an angle. That's what the unit circle and what I'm about to define as the wrapping function, I haven't defined it yet, is going to do for us. So, okay, what does the wrapping function look like? So the functions you're used to thinking in terms of y equals f of x, right? Not necessarily the x adjacent side of a triangle and not necessarily the opposite side of the triangle, right? Just you're used to that symbolism, y equals f of x, where x is the input. So you think of a formula like y equals x squared. You could call that function f of x, and the input is x. If you input 2, what's the output? It's the squaring function. So if you input 2, what's the output? 4. So 2, 4 is an ordered pair on the graph of y equals x squared. If you input 3, what's the output? 9. You're used to functions like that, right? You input a value, and then a single numerical value, you get a single numerical value output. But there are other types of functions. And so this wrapping function is going to have an input and it's going to have an output, but the output's going to be a little different than what you're used to. So the wrapping function, we don't use f to name it, we use w. And we say w of t, the input is going to be t. So you can think of the input as this arc length here in this picture. The crust of the pie. T is the length of the crust of the pie. The output is going to be the point at the end of the crust, if t is positive, going counterclockwise. It doesn't have to be positive. In other words, the output is going to be this point. So you're inputting t, a real number, a length value, and your output's going to be the point at the end of the crust. The beginning point at the crust is 1, 0, but that's not what I'm talking about. I'm talking about this point, which we don't know what it is. So we'll just make it have generic coordinates x, y, because we're in the xy plane. So w of t is just equal to the output is an ordered pair. That's different, right? You're used to the output being a single number. You plug in 2 here, you get an output of 4. This is a little different than what you're used to. The input is normal. It's a real number, but the output is an ordered pair. Input is a real number. Output, ordered pair. So input, real number. Output, ordered pair. And I'll get to why we do this in a second, but okay, so what? It's different. Does it make sense? So you input a real value t, which doesn't have to be considered an angle. It can just be considered a real number. And the output is at the end of the crust. So to draw another picture, if I made t a lot bigger, so let's say I made t, let me do this. Let me erase that. And let me extend this arc over to, say, this point in the second quadrant. So the arc then goes from 1, 0 to whatever this point is. It's the same thing. If that's x, y, we don't know what it is at this point, then the output is that point. So it just happens to be a longer or larger input. Does everybody understand what the input and output is of the wrapping function? Yeah. Oh, the question may come up, why do we call it the wrapping function? Well, because, okay, you see that arc length in purple there? If you straighten it out, it could be like the number line, right? So the idea is this. If you took a number line, a vertical number line, so negative values down here, positive values up here, and 0 on the number line corresponds with 1, 0 in the x-axis, and you bend it and you bend it so that it wraps around the circle here, then say maybe this point up here, it might have to be up here a little further, gets wrapped around to that point. That's why it's called the wrapping function. I think that's confusing, so I don't really mention it when I first talk about it. Really, you just think of the output of the wrapping function as the end point of, if it's a positive number t you're plugging in, the end point of that crust of the pie, or the pizza if you like.